As always, if I don't make sense, please let me know, and I'll be glad to stop and hopefully explain it better. And one other additional thing, for everybody who has come to a boot camp, what you'll get probably Monday morning is an entire playlist of all 13 boot camps as like a thank you for coming out to the boot camps. And so for attending them, you will get that as a resource to potentially study for your exam. Do with it as you like, but it will be all the boot camps compiled in one hopefully nice, easy to use format. And you'll also get a overall boot camp survey, which we turn into the grant people, which you get an opportunity to give feedback on how we can make it better, what you like, what you didn't like about all these things. All right, let's move on. So, as always, all your formulas are over here on the left. And of course, since we're focusing primarily on application, we're going to primarily utilize these kind of concepts in addition to the scatter plot techniques and that kind of stuff, and focus more on just application questions. And let's just dive right into it. So we're going to go into the first question. And so on the first question here, we can see that we're being asked for several different things. And of course, we know there's multiple ways of calculating all this. I'm going to utilize for right now, at least the formula ways and not the scatter plot method, at least until later on. And so that we want for the least squares regression model, if you recall, the general equation form, at least from a statistics perspective, is y hat, because you want to predict y, so we put a little hat on it, equal to b naught plus b1 times x, where this is known as the intercept and b1 is known as the slope. X is your independent or input variable, and y hat is our prediction. And so in order to have our equation, we always need to derive the b0 and b1, or b naught and b1. B naught is just known as the intercept, and Excel has a simple formula called intercept. Sometimes you'll hear it called the constant. It's all the same. And we always do the y's and the x's. And by convention, y's are usually on the bottom or on the right. X's are usually on top or on the left. Another way of thinking about it is which one would more likely influence the other. And so would how much time you spent studying affect your test scores, or would your test scores affect how much time you spend studying? Generally speaking, we would assume that studying results in some kind of test scores effect. So that's how we would kind of relate. And so whatever kind of, not necessarily a cause, but whatever is influencing the other. That's how you kind of identify the X. B1 is our slope. And so again, your Y's and the X's. And so we have a equation in the form of y hat equals 88.8. It's negative, so minus 3.28 times x. And there we go. I'll come back to some else in a little bit later, but let's continue with this for now. So the next thing we want is the r squared. And I'm going to compute it through formula, but of course you can totally get it from the scatter plot, like any of these measurements. So I'm going to get r, so I can have r being squared. And we know how to find r. R is just correlation. So it'll be the y's and then the x's. Technically, for correlation, the order doesn't matter. I just like to be consistent and always do it the same way. And therefore, if you want r squared, you are literally just going to take your r and you're going to square it. And you have r squared. One second. Students asking to be called in. There we go. Okay, back to where I was. So now we have r squared, we have r and all that fun stuff. And they want us to now interpret the slope, part C here. And our general way to talk about it is simply going to be in the following very general format. for every additional X units, and we should say 1 X unit, and I'll show you how to translate this to actual English in a second, we get additional slope of Y. That's a very generic way of doing it. Obviously, if your instructor wants you to have a very particular way beyond this, do it their way. They give you the points, not me. But essentially in this story, the X unit is hours spent online. So I would say for every additional hour spent online, and now it's going minus 3.28. That's my slope, the B1. We lose 3.28 points, because that's the value of the Y unit, on our test scores. We lose 3.28 points on our test score. Some to that effect. And so it's just a matter of identifying the general unit that is defined through X. In this case, the unit was hours spent online. And then the slope was negative 3.28. And then Y is test score. Now, what does it actually mean in context? Well, it means, if you recall, this is the estimated starting value, the estimated average starting value. So you would start at 88.8. And then every time you add 1 to the X, your score should go down by 3.28 points. And so let's just round that to 3.3. Your next score would be around 85.5. And then if I go another hour online, I would go down again by 328, making it something like, again, if I'm calling it 3.3, there would be something like 82.2. And if you did another hour, another 3.28 loss, and another hour, another 3.28 loss. That's why we say for every additional hour, you lose 3.28. And so it's just a way of kind of showing that relationship. The more hours we spend, the time we're losing. And of course, what we can notice then is time is increasing, it's getting bigger, but our scores are decreasing. So of course, it's a negative correlation, which we already knew that because your R is your correlation. And one other fun fact I like to point out to people, one thing you should always notice is your R sign should always, always, always match your slope sign. So if your R is negative, your slope is negative. If your R is positive, your slope is positive. They should always match. If they don't match, you made a mistake somewhere. They have to match because negative correlation means it's going down. A negative slope makes it go down. If they don't match, that means that one is saying go up while the other says go down, which is a contradiction. Okay. Now we're going to make predicted Y values, and we know the prediction is just this formula, right? This is the prediction formula, our least squares regression formula. So we're just going to add a row here. We'll call it prediction. You can also call it, if you prefer, Y hat to be a little more formal. And I generally like to use the exact values. So some people get tempted to use estimated values. Unless your instructor tells you to go that route, I would not do it myself. And so in order to get the exact values, I'm going to cell reference and lock the cells. So I would go equals my intercept, and then I want to lock the intercept by adding a $ in front and behind the R. And then you need to add on your slope because the slope itself is already negative. You don't want to say minus because that'd be 2 minuses, which make it positive. So we say plus no matter what, and then click on the slope. And then once again, add your $ in front and behind the R. And so notice it's intercept plus slope times X. So at the very end here, we can times Rx, which is hours spent online. And now we can go all the way across. And again, we're only doing it this way because we want exact values. If your instructor allows you to round for your prediction equation, then round. It will definitely save you some time. You don't have to lock anything. But always check with your instructor. But now I got a whole list of predictions for that whole row going across. Just checking to see what else we want. We got our predicted values. Now it says find the residual. And so our residual is just defined. Residual is the actual event minus the predicted event, in this case, y hat. We just want to do that subtraction. And if you need it, they actually tell you right here, actually they used to tell you there, they don't tell you there anymore, but yes, it's just actual minus y hat. And so we're going to take the actual event, so when it actually got a 96, and take away what we're predicting to happen. And we now have a prediction, or we have a residual, which is just how much error there was. And so if I take this all the way across, I get all of my residuals. And now let's take a second to understand what these predictions are actually telling us, what these residuals are telling us, after I get a little bit more spacing. There we go. So let's think about it. What exactly is a prediction equation? What does it do? Well, this is just a line, and we know it's decreasing, so it's doing something like this. Because of the negative 3.28, we're losing, it's going down as we go to the right. As x increases, y is decreasing. So at this location of 0, at 0, the line is suggesting that it's 96. Actually, no, it's not. The line is suggesting, the prediction, suggesting that it's 88. So the line at this location is 88. But the reality is that it's up here at 96. So the residual is just telling us how much we need to correct our line by. So in order for this prediction to be right and match the data, it would need to add 7.236 points. And likewise, over here at 3, our line is saying the score should be around 78.9. But the reality is, I'm focusing on this 3, by the way. The reality is this person's score was actually at 74. And so in order to accurately get to that person's score, it would need to come down. It would need to go down by 4.9 points. And so essentially all the residual is doing is showing you how much correction you need. This is how much you would add to the prediction equation to get what really happened. This is how much you would take away from the prediction equation to get what really happened. And so it's just showing you how you would need to adjust the equation. Now, why am I making a big point about this? Well, what they'll do on the exam is they'll say you have a residual of 5, or of 6, I guess I wrote 6. Is that an over or under prediction? And you won't actually have the data, because if you have the data, it's pretty easy to see if you have an over or under prediction. What they're going to do, though, is tell you the residual and then ask you that question. And so you need to know that if we have a line, whatever that location is, you would need to add or go up 6 places to get to the data point. Meaning that the line is underneath that data point. And so a positive 6 would be an under prediction, because you have to add 6 to get to the real result. So a long story needed than it needed to be. If you have a positive residual, and I'll write this down in a second, if you have a positive residual, that means you got an under prediction, and vice versa. So a positive residual equals a under prediction. And a negative residual then means you have an over prediction. And that, of course, assumes that we're defining residual as actual minus y hat. In most texts and most classes, that's how they define it. Once in a while, you'll get a professor from overseas and they'll define it the other way, but in general, we define it as actual minus y hat. So definitely always check with your notes. Okay. So we now have our residual, and now we're going to determine if the model itself is good. In general, when you talk about a good, they want you to talk to 3 things. They want you to know, is the scatter plot good? Is the R squared good? And is the residual plot good? And of course, here they want you to just talk to at least two of them. So at least two of these out of three should be good in order for the whole thing to be good. And in general, unless one of these is overtly bad, we would call it an okay model. And if, like, two of them are good and one's not good, but not terrible, then we call it an okay model. So ideally, all three would be good, but we need at least two of them to be good and one not to be terrible in order to go with it. So we already have the R squared, and there's a lot of debate about what's considered a good R squared. Unless your instructor tells you what that cutoff is, it's kind of open up to interpretation. For the most part, though, we kind of have a general consensus that things in the 90s and 80s is great, and anything less than that is kind of bleh. And then anything really close to zero is terrible. So this is kind of in that middle range, and so this is kind of a bleh. Not really that good, not really that bad. So if I were to talk about the model, I would probably focus on the other two because this one's kind of like in that iffy range. It's not really high, it's not really low. So we really want to focus on these two elements because they're much more concrete on how we can interpret them. So the scatter plot, we're just going to highlight our data, the actual data of the scatter plot, and go insert, and then pick our scatter plot option. And here we go. We got a general line. And I hope we can agree that for the most part, it does seem to be relatively uniform in this kind of range here. And it's all kind of going down. We have this one kind of oddball to the side, but for the most part, it seems to be kind of going down and unified to the right. And so I would argue the scatter plot looks fine. There's some kind of structure to it, and it appears to be going almost like a big fat line going towards the right and down. So the second thing we want to look at is the residuals. And there's multiple ways of doing it. Today I'm going to show you by doing the whole big group selection, like that. And go insert in the scatter plot option. Once your scatter plot pulls up, you want to right click and select data. When the menu pops up on the left, you'll see test score and prediction. Remove those first two options and leave the residual one. When you do that, what's left behind is our residual plot. It's another way of manually doing it without having to worry about highlighting two different rows, like I did last week. And so there's our residual plot on the left. And what you're looking for a residual plot is a roughly 50-50 split. We shouldn't have everything clustered on one side or the other. And it should look roughly random. We don't want to see any kind of nice, pretty pattern in our residuals. If that happens, that's a red flag. If it's all clustered on one side or the other, or if we see a pattern, red flag. It should look relatively patternless. And so, yes, you're basically judging it based off appearance and just your opinion. And it should look roughly 50-50. There is such thing as a residual analysis and a residual test. We're just not going to talk about it in this class. If you go higher in stats, you'll learn it. But, that kind of idea. And so a rough sketch, we could see that we have about, if I ignore the ones on the line, I have about 5 above and approximately 5 below. So yeah, about a 50-50 split. And it looks relatively patternless. So the residual plot looks great. My scatter plot looks like it's relatively uniform and going in a direction that corresponds to my correlation. My correlation says that it should be going down. And this looks like it's going down. So it's all indicative that something good's happening. Now, why am I making that comparison between the two? Well, sometimes you might have data that for the most part is like all clustered around here. And then you have one really high outlier. And instead of having a line that would more appropriately go through the middle of this, because of that one high outlier, you're going to get a line that does something more like this. And so you're going to have a very positive correlation when the data down here is doing something else. And so you can just have an outlier influencing things that don't make sense. And so you should just have like a general understanding that they should kind of like correspond to each other. If your data looks like it's kind of close and going down, then your R better be negative, else there's a problem. And so I would definitely, in this kind of question, talk to the last two things, the scatter plot and the residual, and emphasize them as reasons for a good plot and not R squared here, because R squared is not really going to tell us much because it's not a very high value. It's not really high, but it's also not really low to just exclude it either. So given that 2 out of 3 of these are good and the other one's just bleh, I would call the model relatively good or a good fit. All right, let's move on. Same thing now, but I'm going to go a little faster. And this time I'm going to get the least squares regression model using the scatter plot method. So I'm just going to highlight all my data and go insert, scatter plot. And then from here, there's a few ways to get there, but let's do it by going to the plus sign, point to the bottom, click the arrow on the right, and go more options. Once you do that, you can scroll to the bottom, display your equation, display your R squared, and there's a lot of the information done for us. And here's the only part you have to be careful about because it depends on how picky your teacher is. This equation is written in the algebraic method. That is, they put the slope first and the constant last. So they have the slope here and then the constant. If your teacher doesn't mind it that way, yay, you're done already. If your teacher has a problem with it, and I know the homework sometimes requires it, they always want the constant first and then the slope, aka the coefficient, second. So this is the formal way we do it in statistics, but if your teacher doesn't care, then you don't have to change it. Verify with your teacher how they want it. If they don't care, then feel free to just write that down and call it a day. The only disadvantage that I could think of using this method for the equation in R squared is when I go to type in my formulas, because now I have to manually type these numbers. And so no matter what I try, I have to round. And for me, rounding is just not good until you do it at the very end, because when you round early, it can lead to incremental mistakes. So use this method if your instructor allows you to round for your formulas when you were predicting. If you can predict with a rounded value, then this is absolutely fine and it will save you a lot of time. If they want you to predict with exact values, then you cannot use this method, because then you're predicting with rounded numbers that are not exactly the numbers that you should be using. So definitely check with your instructor if you're allowed to predict with rounded numbers or must you use the exact number to make predictions. But we have our least squares regression at least, and we have our R squared. So let's interpret our slope. Our slope we can see is this positive number. And so what we'll say, for every additional X, and X in this case is online quiz average, so for every additional point earned on our online quiz average, do we lose or gain? We gain because it's positive. We gain 0 point, let's just say 6 points on our final average. And there we go. For every additional X thing, we gain whatever the slope is on the Y thing. It's our general interpretation. Let's make our predictions now. I'm going to assume that they're going to allow you to have estimated values. So I'm just going to use the equation down below. Again, always verify because not every teacher does it the same way. Makes my job difficult and can make it confusing for y'all because sometimes you hear different things. So always check with your instructor because they give you the grade. But assuming that we can use predicted values, I would write that equation times my X and hit enter. And again, if I didn't use predicted values, that's when I would write slope and intercept and then lock the cells like on the previous page. Take it all the way across, and we have our predictions. Maybe too many decimals. We'll just keep it rounded like that. And then we can, of course, now we can find our residuals because we know they're going to ask us that in a second. And we'll have our actual score minus the predicted score. Take it all the way across. And of course, when you see the dollar sign, it means the cell is too small. So you just make it a little bigger. Or the hashtags, not dollar signs. And we just did D and E. We just did the equation, or the prediction and the residual. So now we're ready to find out if this thing's any good. We already have a scatter plot in front of us. That's one advantage about doing this method. And we see the regression line going through, and it all seems to be relatively following that line. So yeah, the scatter plot looks fine with no incredible outliers. It's a good scatter plot. Our residual is kind of good, you know? It's not really at the 80-90 range, but it's not terrible, so it's kind of good. What this residual is telling us is that this line, not the residual, I'm sorry, what this R squared is telling us, the coefficient of determination is telling us, is that this line here is roughly explaining about 75% of the variation in the dots. It explains roughly 75% of how the dots change from as we go to the right. And so if we were to kind of like roughly estimate how it's changing, that line captures about 75% of that movement in that direction. And so that's a pretty good chunk of it. We like 80 or 90, but it's darn close. So far I know the scatter plot is good. R is pretty good. Now let's find the residual. And let's graph it the other way this time. I'm going to highlight the X's, let go of my keyboard, hold down Control, and then highlight the residuals. So you can do it this way or the first way I showed you to get your residuals graphed. Go to Insert and Scatter Plot, and there's your residuals. And again, it should be roughly 50-50 split and look relatively random. Why should it be roughly 50-50? Well, the goal is that your line here should be going roughly between the dots. And so half the dots should be above it and half the dots should be below it. If not, and your line's like incredibly missing it, it's doing something like this, then you're going to have a lot of dots below it. And that's a red flag that your line is tilted funny. Maybe because you have one really high dot pulling it up. Or if your dot is going the other way, if your dot line, was like way over here, then you're going to have a lot above it and very little below it. And so these are just indications that your line is like turned wrong if that's happening. And then in addition to, we also want to see randomness because it should be, random where it kind of how bad it misses them. We want to miss everything relatively equally and not in any kind of uniform pattern. Because if it's patterned, what that means is that there's another type of behavior going on here that is being missed by a linear graph. So we want it to be roughly 50-50 to show that it's shown that, balance between the dots, but we also want patternless to show that a linear graph is the best estimator. And so, yeah, the residual for me at least looks relatively random and patternless and about 50-50 split. And so we're happy. And so again, I would definitely talk about the scatter plot and the residual, and the 0.75 is roughly R squared isn't too terrible either to mention. So I would mention all three things in terms of how I would describe it as being pretty good. All right. We have age and IQ. We want to find the correlation between the two. So let's just say Corel. I always do Y's and X's, but as you know, for correlation, it doesn't matter. And we get a number that's really, really close to 0, but negative. So since it's really close to 0, our general relationship is that we would call it a negligible relationship, which just means almost no relationship. Can't say no relationship just because it's not 0. And I should be really clear here. It's not just a negligible relationship, it's a negligible linear relationship. Because all we know from the correlation is a description on the linear behavior. There may be another behavior that's nonlinear. So we're essentially saying that age seems to have no impact on IQ. And so if I want to write that out in a sentence form, I would just say that. I would say that it appears that age has little to do with IQ. Okay. Which one is the implied independent and dependent variable? So logically, are we trying to say that age, would influence IQ? By convention, yes. Typically, whatever's first is usually identified as your X, and the second one's your Y. So what's implied about the setup is that age should be our independent and our IQ should be dependent, even though we showed right here that it appears that they don't have that relationship. We're at least trying, based on the setup of the problem, that's implied that that's the orientation. So now what is the slope and what does it imply? So let's find the slope. Slope, Y values, X values. And so the negative 0.02 implies that for every additional year of living, I guess, you can find a better way of phrasing it, but for every additional year that you're alive, we lose 0.02 IQ points. So for every additional year that you live, you get dumber, is what it's trying to say, in an IQ sense at least. Now, what's the y-intercept and what does that imply? Let's find it. Intercept, y values, and our age values. So that implies that at birth, we have an IQ of 108 points. But this is beyond the scope of our data. Remember that second part. It's really important because our data has a range, the lowest number to the highest number of 8 to 71. And so even though this is the definition of what the thing means, that first sentence is 100% what it means, we're technically only allowed to talk to anything from the age of 8 to 70. We have no idea about anything that happens before 8 or anything that happens after 70. We only know that little range. And the intercept assumes that the X value is 0, which is definitely lower than 8. And so it's beyond the range. So we can't actually report this as an actual value, but its meaning is literally this sentence. So technically you'd want to say both facts because yes, that is what the meaning of the intercept is. It's just not relevant as a predictive value because it's beyond the scope of our data. Our scope is from 8 to 70. It's all we're actually allowed to talk about. All right, the linear regression equation. So we have y hat equal to our intercept minus, because it's negative, 0.02x. So if we were 4 years old, what would we report? Nothing. We can't report on a 4-year-old because it is beyond our scope. We're only allowed to talk from 8 to 70 years old. So you better not report anything about a 4-year-old. So instead, if we were to give a report on the study, what IQ should we report predicted as a predicted value based on the study? So in other words, we can see that the correlation is negligible, which implies that if we were to do the scatter plot or the residuals or the other stuff, there'd be a red flag somewhere. And we'll do that in a second to show it. But what do you report then? What's your value that you should report for IQs if the model is bad? But before that, let's actually prove once and for all that the model is just bad. And so we're going to need a couple of things. I'm going to add a row here. There we go. And the first thing I can get is my r squared, because we already have r. So it's just going to be this r up here, literally squared. That's our r squared. And that's virtually 0. So I can actually stop right there if I want it and say, because the r squared is almost 0, red flag, the model's terrible, throw it in the trash. Do not use a linear model to describe this data. But just so we have it and practice it, let's go ahead and do all of it. Let's get our scatter plot. go insert in a scatter plot. And look at that. That scatter plot is really random. Scatter plot should be relatively uniform and following either upward or downward pattern. So the scatter plot is also terrible and trashy. And now let's get our residuals. Let's get our predictions and then get our residuals. So again, your prediction, let's just use our rounded values, 108 minus 0.02 times the input. Take it all the way across. And now we can say actual event minus predicted. Take it all the way across. And we need to graph our age and our residuals. Insert scatter plot. And so if I looked at just the residuals, notice that the residuals, at least in my opinion, look relatively random. So now let me grab it. Hold on. There we go. It looks relatively random and, about equally split. So the residual looks fine. But that's why we have that rule of at least two good things. And so the residual looks okay. It looks about equally split and relatively random. Residual looks fine. But the scatter plot is terrible. And it's interesting how they both look almost identical here. And the R squared is also terrible. So we have two bad things, but this one's, of course, really bad. Does this say that the model should be thrown in the garbage can and we shouldn't use it? And since two things are bad and only one thing is okay, we should definitely not use this model. So then if we're going to predict about IQ, what do we report? We can't use the model. We can't use the equation. So what do we report? Well, you actually already know this answer. All the previous units leading up to this class have all been about single variable statistics, one distribution statistics. And so essentially what we're saying is that we can't use age to talk about IQ. So if I want to talk about IQ, I can only use IQ to talk about IQ. So if I only have this one set of data, only the IQ data, how do I talk about a prediction for IQ? Well, what would we know about IQ? What do we know about scores in general? We know that scores in general should cluster around the center. It should be near the center. And of course, what is a good way to measure center when you have continuous data? An average. So when the model's terrible, you should just take the average of whatever you're trying to predict. If I'm trying to predict IQ, I should just take the average of the IQ. And there we go. And so if we had to predict what the average IQ score was for any age, because we know that age has almost nothing to do with IQ, we should say it's about 107. And there you have it. So again, if you cannot use a regression model, you fall back on what you've been learning to this point and just take the average of that distribution you're talking about. Okay. Coefficient of determination, that's just a fancy way of saying R squared, which we've already calculated. And so what does it mean? It means how much of the variation or how much of the change in the graph as you go to the right is being explained by a linear line. And so if we turn on this line, trying to turn on my arrow, there we go. If I show this line, there we go. This line and how it's going down slowly to the right is only explaining about 1% of the change in these dots. And, so if the dots are doing something else, only about 1% of that progression is being described by this line. And so that line is terrible in terms of trying to describe how the dots change as we move to the right, what we call the variation between X and Y. As you move in this direction, how well is this line here capturing what's happening to the dots? It's not doing a good job at all. It's only describing about 1%. So what does it mean? If you want the formal definition, of course, you can go see what I put here as a definition for you. If your teachers give you one, but regression just compares or describes the variance in the dependent variable. relative to the independent. So yeah, it's just literally the change between the two facts. It's only about 1% of the data is being explained by that line. One of the reasons why we should throw it away. All right, last one here, y'all. We're going to find the linear correlation. Let's just do it up here. So we have equals correl, y values, x values. There we go. Interpret it. That's a very close to 1 number, so we can call it a strong positive. And we should look it up. We'll check, we'll verify it in a second. So the only part we don't actually know without the scatter plot is linear relationship. We don't actually know the linear part without a graph. So let's actually just add in the scatter plot and verify that linear does make sense. And yeah, I hope you agree that minus that one random dot to the side, it does look linear. With that one kind of outlier out on the side there. So relatively tight and uniform with this one exception. And so yeah, so we can definitely say a strong positive linear relationship without much reservation. Okay, so now we're ready for the regression line and equation. Let's just go ahead and turn it on this time. Trend line, more options, scroll to the bottom. There we go. I went ahead and add the r squared for good measure. And you can always check it. If you simply square your r, you should have r squared, and that number should be the same one on the graph. And there it is. It's literally the correlation squared, nothing special. But notice what it says, 92.15. So 92% of that change in the dots is well explained by that line. Obviously not 100% because the dots aren't on it perfectly, but darn close. So a lot of the data is being explained with that line. Okay, now we're going to do some predictions. Because I have the estimated values there, I'm going to use rounded values for my y hat here. So now we have, I'm going to do the classic way of the constant first, and then the coefficient or slope second, times the input, take it all the way across. And of course, let's get our residuals, because you know they're going to ask you. Never hurts to, at least, even if they don't ask you. Actually happened minus the y hat. And now we have a bunch of stuff done. So let's see. Found the equation, predict it for 160. So I guess I should have just read ahead. They want us to do for 160 though. So let's just add 160 to our list. And then we could scoot down our bottom two informations. Oh, can't do the residual though because we don't know the actual. There we go. So we have a prediction of 26.4 from a horsepower of 160, but we got to be careful because we want to convert it to thousands. So the answer is not actually 26.4 unless I put 26.4 thousandths. More traditionally, what you would do is simply times that by 1,000 to know the right price. So maybe I'll do that over here. 26.4 times 1,000. And so now I can go to home and turn this into money and see that the actual value that we predict for a 160 horsepower car is $26,403. And one thing I didn't mention that I should check, you should always check, of course, that this value is in the scope of your data. And yeah, minimum number 75, maximum number 230, so 160 is in that range, so I can talk about it. If it wasn't, like I did in that previous problem, I would say can't do it and move on. All right, last question of my bootcamp series. They want us to make a prediction for 129 and compare it to an actual event. So in other words, we're looking at the residual. So let's add it to our chart again. 129. They're saying the actual price on it is 15,000. So I'll just write 15 here because it's in thousands. And now I want my prediction, so I'm just going to bring it over 1 square. Of course, you could just manually type it in if you like, but there's our prediction relative to what the price would be. And so if I found my residual, of course, what actually happened minus what I'm predicting to happen, and I see a negative residual, which of course means an over prediction. And yes, I know. You could also just look and say, well, 21 is bigger than 15, so it's an over prediction. I just remind people because sometimes they're just going to show you the residual. Either way, we're predicting too high. We're saying that you should expect to pay $21,000, and Hyundai's like, well, by the way, our car's only 15, so it seems like a good deal. So take with that what you will. And there you go, my friends. That's regressions and correlations in a nutshell. That's a lot of application for it, at least. Last week was all theory. If you want that video, just send me a little message. As I mentioned at the very beginning of all this, on Monday, expect a overall bootcamp experience survey for any boot camps you've attended, just kind of reflecting back on what we could do better and or not in the future. And you should also get a bootcamp playlist for all 13 boot camps so you can utilize that to study or do with it as you will. Watch them, don't watch them, 100% up to you. But that's everything. Good luck. Have a great day.